Hi everyone, this is Professor Iris Miano. This is Math 2 Pre-Calculus Day 1 lecture. We're going to be covering several examples that pertain to review material, things that you probably already know how to do coming into this class. I just want to remind you of a few things that I would think are pertinent with particularly the first chapter that we are going to be exploring once we're done with our review sections, and that's going to be chapter 1 covering functions. So let's go ahead and dive into this first example in which we will be solving a couple of equations. And I picked some of the more challenging ones. I figured that solving linear equations, quadratic equations, even third degree equations that have four terms are things that probably everybody remembers how to do, knowing their factoring schemes and things of that nature. Here is a rational equation and a radical equation. So we'll do one of each of those. I'll remind you of a few tips that will get you through the process, and then we'll move on to some inequality stuff. Here we go. Here's the first example. So you'll notice that these rational expressions in this equation both have denominators of x minus 2. So what I suggest that you do to solve this equation is multiply both sides of it by the LCD, which is the binomial factor of x minus 2. I'll write that off to the side. Upon multiplying both sides by this LCD, you will have the x minus 2's in these denominators that I'm covering over with my stylus here. They will cancel out, and you will have the following left. X plus 3 times the quantity x minus 2 is equal to 2. So I'm not showing all of my work here. This is just the result of multiplying both sides of the equation by x minus 2. If you'd wish to see more detail, you can ask me to perform the further detail example of this in lecture. Okay, distributing through the factor of 3. We need to do this in order to gather up all of the x terms together and put them on one side of the equation. That's how you solve for x. Here we go. X plus 3x minus 6 equals 2. Now we can combine the x terms on the left-hand side, and we will get 4x minus 6 equals 2. Let's go ahead and add 6 to both sides. Let me give myself a little bit more room on the page. And we will be left with 4x equals 8. Divide both sides by 4 in order to get your value for x. And that means x equals 2. But hold on a second, guys. We were dealing with a rational equation to begin with. And rational equations, if there is an x value in the denominator space, have limited values that x could be, because you don't want to have any zeros occurring in a denominator space, because that makes the rational expression undefined. Now look at the value of x that we calculated here. X equals 2. Plug that into either of those rational expressions. Yes, yes, yes. And you will get undefined rational expressions. So even though x equals 2 was a calculated solution that we came up with, we actually have to deem it extraneous. So I'm going to actually cross it out and report that this equation has no solution. You can go ahead and exemplify that with a little circle with a slashy, or you could say no solution here. Again, rational expression or rational equations. Something to look out for. Make sure you check your final answer to see if it actually is viable. In this case, our final solution was not viable. All right. Moving on to the radical equation. Let me give myself some room here to work. We need to understand that the name of the game is getting these radical expressions separated by the equal sign. So my first move is actually going to be adding the square root of x minus 1 to both sides of the equation. And the result there will be the square root of 3x plus 1. is equal to 2 plus the square root of x minus 1. Okay, now that we have radicals on both sides of the equation, it is appropriate for us to square both sides. How does that look? Well, I'm going to add that in red. Squaring both sides. And you got to square the entirety of both sides, and it'll be easy enough to deal with that on the left-hand side because the square root and the squaring are inverse operations of one another. They cancel each other out, and we will be left on the left-hand side with 3x plus 1. On the right-hand side, it's a little bit more complicated, but nothing we can't handle, provided that we remember squared binomial product rule. So that will give us the square of the first term, so 2 squared will be 4, and then 2 times the product of the two terms is the next term, so that'll be 4 times the square root of x minus 1, times the square of the last term, which will simply be a quantity x minus 1, which you could have in parentheses or you could drop the parentheses. Doesn't matter at this point in the game. Let's go ahead and combine like terms, essentially the 4 and the negative 1 on the right hand side, and we'll get 3x plus 1 equals 3 plus 4 times the quantity x minus 1 plus x. At this stage, you will want to combine all of your like terms on one side of the equation, and by that I mean let's go ahead and subtract 3 from both sides and also subtract this x. That way we will have all of everything that's not associated with this radical term on one side of the equation, and we're going to yet again square both sides. Here we were left with 2x minus 2 is equal to 4 times the quantity x minus 1. Now why do we want to do that? Well, we need to free up that last x and still it trapped inside of a radical. So squaring both sides is going to allow us to do that finally for reals the second time. Let's go ahead and I'm going to continue my work on the other side of this page just to keep it all on the bottom part of this page here. And let's move back over to blue, and that'll give us, remember your squared binomial rule, that'll give us 4x squared minus 8x plus 4 on the left hand side, and then here we'll square both the 4 and the square root, which will essentially just be taking off the square root there, because the square root and the squaring, again like I said before, are inverse operations of each other, so we'll get 16 times the quantity x minus 1. We will need to distribute through that 16, and we will get let me maintain my color scheme here, 4x squared minus 8x plus 4 equals 16x minus 16. Now let's get everything on one side of the equation, see if we can factor, and then use the zero product property to determine the solutions, if any. Okay? Subtracting 16x and adding 16 to both sides. Will yield 4x squared minus 24x plus 20, it's supposed to be a plus right there, equals 0. Now, factor. Is there a GCF? Sure enough there is. Let's take that out first. 4 times the quantity x squared minus 6x plus 5, and the quantity that's equal to 0. Go ahead and factor the trinomial inside of the parentheses. You can do that using the diamond method. Let me go ahead and briefly demonstrate what that looks like. You're going to put the b value down below, that's negative 6 here, positive 5 there. So what two numbers multiply to give you a positive 5 but simultaneously add to give you negative 6? Well, that would be negative 5, negative 1. So that gives you the factored form of what's inside the parentheses here. So that'll be 4 times the quantity x minus 5 times another quantity x minus 1 equals 0. Zero product property determines that the two solutions are x equals 5 or x equals 1. You'll want to check to make sure that these fit back into your radical and indeed give you the right solution. And they do. Oh, I want to get this as the thing that I box up my answer with. Okay. I've already checked them ahead of time, but yes, sometimes the solutions that you calculate might, when you plug them back into the original equation when they're radical equations, might get you numbers that are, or sorry, they might be imaginary, in which case they wouldn't be real number solutions. And for something as simple as just a radical equation, you're going to be looking for real number solutions only. So if they create a negative number in the radicand, so inside of the radical, then you're going to say you have no solution. But both of these are viable solutions. If you plug them in, you find that they will indeed work out. Okay, let's go ahead and solve another equation, a formula to be precise, for a particular variable. So here we're going to solve for r. So I'm going to go ahead and point at r just to highlight it there. You'll notice that it's being multiplied by t, it has 1 added to it after the fact, and then it's stuck in some parentheses. So how do you free it up from there? You can either divide both sides by p in order to get rid of that factor outside of the quantity, or you can distribute through the p and then work from there to isolate r. Personally, I like to divide both sides by p when I see stuff like this, so that's how I'm going to do it. Divide both sides by p, and I will be left with a over p is equal to, because both of those cancel, and you can get rid of these parentheses at this point, 1 plus RT. Okay, then again, we're trying to isolate r, so the next thing that I would do is subtract 1 from both sides. Now, you won't be able to subtract 1 outright from the a over p because they're not like terms, but you can get as close as possible with that by just representing it as a over p minus 1 is equal to RT. And then lastly, go ahead and divide both sides by t in order to completely isolate r. Okay, so that'll get rid of these t's right here, and you'll be left with r. And go ahead and feel free to pancake flip that equation so it reads nicely as r equal to, sorry, let me go ahead and get that in blue. Yep. R equal to a over p minus 1 all over t. And that'll do it. If you decided as your first move to distribute through the p instead of dividing both sides by p, your final answer could look a little bit different than mine, but as long as you performed all of the properties of equality in order to isolate r correctly, you should have a final answer that is equivalent but looks a little different. If you'd like to see that alternative markup, just let me know in class and I'd be happy to do it in a different way. Okay, so that's solving equations. Let's go ahead and dive into some review on solving inequalities and graphing, interval notation, all of these good things. Okay, so remember your properties of inequality. If you ever encounter multiplying or dividing both sides or all sides of an inequality by a negative number, remember you must change the direction of the inequality. If it behooves you to pancake flip your inequality so that it reads better with the variable coming first as you read it from left to right, make sure you change the direction of the inequality in that case as well. I will highlight these ideas as they come up in these examples. Okay, so this first one, it looks like it got a little bit, what's the word I'm looking for? Strange because it needed extra room. Okay, but here we go. Okay, let's look at the following number line graph. Notice that 0 is marked on the middle-ish tick mark, and that none of the other tick marks are labeled, but the assumption here is that every tick mark is marked by a unit distance away from the previous one. So we have a bracket on the 0, and then what tick mark appears to be having the parenthesis in according to the graphic? Well, that would be the number 3. So I'm going to go ahead and exemplify that with a 3 right there. Just draw it on top. And we are to express the graph shown in blue using interval notation and as an inequality. So let's start with the interval notation because the same symbols and numbers that you would use in interval notation are here on the graph itself. We're going to take first the bracket and the 0. That's the lower bound. That's the smallest value that the solution set could take on. Put a comma there and then grab the upper bound of 3 and encapsulate it in a parenthesis because that's the symbol associated with the 3. And it's really just that easy going from graph to interval notation for this compound inequality. And as far as the inequality is concerned, just say to yourself, okay, x, which is the variable we need to use, is somewhere between 0 and 3. And anytime you have a bracket, you need to have the inequality symbol associated with that have a little horizontal line underneath the inequality symbol indicating that that endpoint is part of the solution set. And that's done. Here was the interval notation check, inequality check. Done and done. And I think we're ready to move on. I have another example with these same instructions. Notice that I have 0 marked as the tick mark in the center, and so this bracket is occurring at -2, and it appears to be going off to -infinity. That's what happens when your trajectory of your solution set, here marked in blue, goes off into an arrow in a certain direction. This is -infinity, this would be infinity over here. So in order to do the interval notation, you just start from left to right, your lower bound being technically -infinity, although it's not bound. And you always want to cap off positive infinity or -infinity bounds with a parenthesis. And then we go all the way up to -2 and cap that off with a bracket as indicated by the graph. Similarly, but a little bit different. As far as the inequality is concerned, you want to say to yourself, can I verbally describe what's going on in this graph? And if you say something to the effect of, well, I want to capture everything less than or equal to 2, or -2, that is, less than or equal to -2, then, you'll just say that x is less than or equal to -2. So having some familiarity with this is going to be advantageous to you, but here's a little brief overview on how to tackle that. If you have any questions, feel free to, write them on your notes and margin and go ahead and ask me in class. All right. Let's go for this next one. Write each inequality using interval notation and graph it on the number line. Okay, I would recommend you graph first and then do the interval notation. That's just my spiel on it. So if we want to go from -1 to 5, we need to find where those tick marks are on our graph. Here is where -1 lives. And here is +5 all the way over here. Okay, so in negative, we're going all the stuff in between. We're going to include -1, and that's how I'm going to do indicate that is with a bracket. We're not going to include 5 because there's no horizontal line under the inequality symbol, so it needs to be captured with a parenthesis. And I could go a couple of times over just to really make this thicker in the bracket. Capture everything in between. And there you have it. I've graphed it, y'all. There's a graph. Check. Interval notation. Let's go ahead and take that from our graph. We have a lower bound of -1. We're including that endpoint, so brackets appropriate, comma, upper bound of 5. Put a parenthesis on that because we're not including that endpoint. And check on that one as well. Let's do one more of this type, but have it be open-ended. We are strictly going to be greater than -4. Where's -4? 1, 2, 3, 4, right here, this tick mark. And we're going to be greater than that. So parenthesis is appropriate, and we're going to grab everything to the right. Because if you're greater than some number on a number line, you're moving to the right. And since there's no upward bound, we're going to color in this arrow, and we're going to go off to positive infinity. So lower bound's -4. Read this graph from left to right. Parenthesis on it, because we're not including the endpoint, and we're going off to positive infinity. And always cap off positive or negative infinity in the interval notation with a parenthesis. You should never have a bracket on positive or negative infinity. Okay? Great. And moving on. Now let's say we have the solution set in interval notation to begin with. How do we graph it and how do we write it as an inequality? I would graph it first. The endpoints are 1 and 2. I'll go ahead and exemplify those on the number line. They both have parentheses, and you want to color in everything in between. And this is to say that x is between 1 and 2. And that is that. Hopefully that wasn't too fast, but if it was, ask me to slow down in the lecture discussion. Let's do this one more time. We're going from negative infinity up to 3. Where's 3? 1, 2, 3. Let's graph that on our number line. Okay. If we start off with negative infinity, we're going off, in that direction. And then we want to capture everything up until 3 and including it. Let's put a little bracket on your 3, like so. And color in that number line. Forever and ever and ever in the negative sense. Okay, and then just say to yourself, all right, what is this graph showing me? It's saying that all of my x's that I want to grab that are possible are less than or equal to 3. Okay, great. Moving on. Let's solve this inequality and express the set notation and interval notation and graph it. Okay, so previous problems have already had the inequalities be solved if that's what you were first given. This one's going to require some work. So we need to find the LCD and multiply all sides of the LCD or of the inequality by the LCD of 6. And in doing so, you will get, if I'm not mistaken, 2 is less than or equal to 3 times the quantity x plus 1, which is less than, if I multiply 2/3 by 6, the 3's will cancel and I'll be left with 4. Okay, let's distribute through the 3 and we will get 3x plus 3 is less than 4. Subtract all sides by 3. And we will get negative 1 is less than or equal to 3x, which is less than 1. And then we got to divide all sides by 3 to end it. Hold on. There we go. Great. So then x 1/3. Great. So we have this 0 highlighted here. We can label the tick marks however we see fit. Usually the convention is 1 tick mark equals a unit distance, from 1 tick mark to the next, but you can certainly change that. I'm going to go ahead and let this third tick mark be a 1 to the right of 0, the third one to the left of 0 to be negative 1. So that way, this tick mark right here is negative 1/3, right? And this one is positive 1/3. And that'll allow me to, with relative ease, graph this particular inequality. And it looks like I have a bracket on this side because I'm including the negative 1/3. Put a parenthesis over here. And I'm going to color everything in between. And that'll lend itself nicely to the interval notation of negative 1/3, comma 1/3, parenthesis on this side, bracket on that side. Cool. And that's all the inequality stuff we wanted to cover. Cool, cool, cool. Moving on. I have, in section 2.6, I wanted to do a word problem with a quadratic model. So a quadratic model is a parabola, okay? And this suspension bridge problem is extra fun because you can build off of a drawing. That's the most effective way that I see to tackle this problem. So here we go. Let's just go ahead and dive right in. And again, the section is very telling as far as what kind of equation we should expect to deal with here. It's a quadratic. So quadratic models are y equals ax squared plus bx plus c, or something even more simple than that. Like if our particular equation happens to be centered at the origin, which PS, hint, 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 that's what I'm going to suggest that we do for this particular problem. Not that you would know that ahead of time. I'm just saying that based on already reading the problem previously. Okay, so let's read the problem together. It says a suspension bridge with weight uniformly distributed along its length has twin towers that extend 75 meters above the road surface and are 400 meters apart. Okay, so here's your bridge, and here are your two towers. Each tower is 75 meters. 75 meters. This is 75 meters as well. And the bridge itself is 400 meters apart total. The cables are parabolic in shape and are suspended on top of the two towers, and the cable touch the road at the surface. So it looks something like this. Excuse my really shaky drawing there, but it's a parabola, okay? It touches right here in the center. And we want to find the height of the cables at a point 100 meters from the center. So from the center, here is 100 meters from center. So basically, we want to find the height of this point. So what is this height? Okay, what I suggest that you do, and I'll do it in, I guess, red to make it really pop, is that you think about this scenario in terms of an XY plane in which the road itself is the x-axis and the center goes through the y-axis. If you do this, I think it's a lot easier to think about what's going on here, in which we have a parabola, an upward facing one, that has its vertex at the origin, in which case we're dealing with y equals ax squared situation. And again, if you were thinking about this and you're like, I wouldn't have thought of that, do not fret. I definitely can go over more examples of this ilk and explain more how this came about in my mind, I guess. So what we want to do is find yourself a point that you know has to exist in the scenario and use that to plug into here to find the value of A. So maybe we'll go ahead and say, well, what's the XY value of this point? It'll be, well, your x goes out to, if this whole distance is 400 meters and the center is exactly halfway between the two towers, then what's the distance from the center to one of the towers? Well, it's going to be 200, right? So that'll be a 200 in the x position. And then, of course, the height that we just determined here was 75. Okay, so plugging that into this equation here, we have, 75 equals A times 200 squared. If you plug this into your calculator, work it all the way down, you will find that A equals 0.001875. Oops, 75. Let me go back. Small number, right? Okay, but we're going to use that. So now the model becomes y equals 0.001875 x squared. And we can use that to find the height when x equals 100 meters from the center, right? Okay, so y equals 0.001875 times 100 squared. And you will find that in that case y equals 18.75 meters. That's going to be the height that you're looking for there. Okay? Fun problem. I like that one. Okay, we just have two more problems that I want to present to you, and then we'll be done with this lecture. And they come from Polynomial rational inequalities. Okay, so what's fun about rational inequalities, and in order to determine the solution set, is that you need to look for critical points. I call them CPs for short. And you want to do a sign analysis in order to determine what the solution set is. Okay, so essentially you want to be looking for when the denominator equals 0 or when the numerator equals 0. Okay, and we'll do another one right there if we feel like we have time. So let's go ahead and draw a number line. I want to do this in black first. And and so let's first determine our critical points. They will be when the numerator equals 0, that's going to be when x equals 3. And then when the denominator equals 0, that's when x equals -1. So we want to graph these on our number line. So if this is 0 right here, then -1 is right here, and 3, 1, 2, 3 will be right there. And you can have some other tick marks too, it doesn't matter. So what we want to do, and I'll go ahead and change the color to blue for stuff that I think is going to be relevant for this next part. You want to have representative values that you test in these in between these two critical points, right? So really it's like this are your regions. So what test do you want? Well, in this region, the smallest integer is going to be -2. So I think that should be the test. Here, anytime you have a region that encompasses 0, I feel like 0 should be the testing point. And then here, we want the smallest integer possible above 3, so I would go for 4. You want to plug these values into your expression right here and determine what the sign is, right? If it's positive, then it works, right, in this particular inequality. If it's negative, then it doesn't work. So here's how it works. Okay, so notice that you have a numerator value. When -2 is plugged in for x, -2 minus 3, well, that's a negative numerator, right? So I'll put a negative sign in the numerator. That's supposed to be a division bar. -2 in the denominator is going to be negative. 2 plus 1 is negative as well. So that's going to be positive ultimately. And as far as the sign goes for plugging in this representative member, so this region's going to work out. So you want to capture this region, but you want to actually leave this open, right? Because the -1 value is not something that's available for you. Being that when you plug it in, it's going to give you a 0 in the denominator. We don't like that. So I did initially put a closed dot, but I modified it slightly with this big open dot. Now we want to plug in 0 and test that. So here's the division bar. When I plug in a 0 for the numerator, that's negative, but a 0 in the denominator is positive. So ultimately the sign here is negative, and we want the rational expression's value to be positive in order for it to work. So we know that this does not have anything to do with the solution set. Again, 3 has to be open because we are not equal to 0. We want to be greater than 0. And plugging in a 3, we get 3 minus 3 is 0, which is positive, and a 3 plus 1 is positive in the denominator, or it's neutral at best, right? Oh, sorry, we're plugging in 4. 4 rather. 4 minus 3 is a 1, that's positive. Sorry, I misspoke earlier. And 4 plus 1 is 5, that's positive down below. So that's positive again. We want to capture this area and go off to positive infinity there, and going off to negative infinity there. So basically you want to just capture everything that you see in this graph that we've done here and say that the interval notation solution for this inequality is going to be negative infinity to -1. And we're not going to include it, but we need to also unify that. So this is a little u with 3 up to infinity. Okay, cool. So, we went through that a little bit of a choppy way. Let me go ahead and do another example for you. This one's going to be a little bit more involved because we actually have to do some algebra ahead of time, getting everything on one side of the equation, making the LCD happen, all that good stuff. So let's first start by subtracting 3 over x plus 1 from both sides. So we'll have 5 over x minus 3 minus 3 over x plus 1 is greater than 0. So the LCD being x minus 3 times x plus 1. So let's go ahead and perform the subtraction here, making the LCD happen. So that'll be 5 times the quantity x plus 1 minus 3 times the quantity x minus 3. If more explanation is required onto how I'm getting this first step going, by all means ask me to elaborate in lecture. Okay, so let's go ahead and distribute, combine like terms, and then we'll determine what the critical point should be. So that'll be 5x plus 5 minus, it's supposed to be plus, 3x plus 9. So that'll be 2x plus 14, x minus 3, x plus 1. Okay, so now that we have everything simplified and on one side of the inequality, and we want this all to be positive, we're ready to determine our critical points, which are going to be when the numerator is equal to 0, so that'll be when x equals -7, so I'll put -7 as a critical point, and also the two instances in which the denominator would be 0, so that would be at x equals 3 and x equals -1. Okay, so we actually have 3 critical points this time, and we want to put those on our number line. Okay, so where do they exist? -7, we'll have this all the way at the end. Let's say -1 is right here, and then 3 is right over here. Tick marks in between, kind of irrelevant, so long as you have your areas well figured out. And okay, and all of these critical points need to be open. I kind of flubbed that on the previous example, right? And we're going to test these 1, 2, 3, 4 regions technically. The tester point for to the left of -7 will be -8. Tester point here should be, I don't know, -2. Any value in between -7 and -1. From -1 to 3, definitely choose 0. On the right of 3, I'd go as small as possible, and taking integers whenever possible. So those are my test ones, my test points, and these are the regions. I'll go ahead and kind of separate them. And let's do our sign analysis. When we plug in -8 into this inequality here, what do we get? Well, -8 will give a -16 here, plus 14 will have a numerator of -2, so that's negative. Down below -8 here will be negative as well, and -8, -7 will be the result of plugging it into this quantity. So that's 3 negative signs, so ultimately that will be one big fat negative. Do we want that? Does that satisfy the inequality? Well, no. This whole thing is supposed to be positive, greater than 0, right? So we're going to say that this region is a no. Okay? From -7 to -1, our representative value is -2. -2 in here is going to be a positive, right, for the numerator, positive. -2 will make it negative here, and negative there. Okay, so negative times a negative in the denominator makes it positive, positive numerator that's ultimately positive. So we want to capture that. It is giving us something that's greater than 0. So this is good. It's part of the solution set from here to here. Okay, I have a sneaking suspicion that 0 is not going to work out, but let's go through it with the sign analysis. 0 will make a positive numerator, a negative for this quantity, but positive for this quantity. Ultimately, the sign here is negative, so that's a no-go for this region. And 4, if we plug it in here, will be positive, positive, positive. Positive numerator, and then 2 positive factors in the denominator. That'll be positive ultimately. So we will go from 3 off to positive infinity. So check out our graph. Everything that's in blue, we want to be able to label, and that'll be going from -7, not including that endpoint, all the way to -1, also not including it. And then we want to unify that with 3 and going off to positive infinity. Okay, so this concludes all of the examples that I want to cover in lecture today to get you started with the review sections of homework. Again, we're just really in review mode, so hopefully a lot of these things were familiar to you, and if indeed they were not, this can be ample discussion for us to have in the lecture proper. Okay, great. Let me know what your questions are.